Okay, hello, do you hear me? It's my honor and pleasure to introduce Professor David Kazhdan from the Hebrew University of Jerusalem in Israel, who is going to give us today's lecture, whose title you see. And I would like to add that in human culture, mass including, we have equally important written and oral traditions of advancing our cultural knowledge. And David's multitude of seminal papers over the last 60 years constitute his amazing and well-known contribution to this written tradition. But his contribution to the oral tradition is simply unprecedented due to his unrivaled ability to talk with many people and instantly understand mathematics and immediately come up with ideas which often change the development of the subject in that area for the years to come. So please.
Okay, the talk is on the cosmological constant in the perturbative supersymmetric string theory. I have to say I'm not a physicist at all. But as I heard, people working in the string theory expect the cosmological constant to vanish. The cosmological constant is written as a formal sum where h is a parameter, and the genus contribution AG defined, say, as the integral over superdensities. The quotation marks on defined is based on the difficulty to define this integral. The absence of a definition of integral of superdensities, which are not compactly supported, creates a problem. The necessity to provide a definition of such integrals is the reason for revisiting the computation I2, which corresponds to curve genus 2, which was apparently performed by de Hocker and Fong more than 20 years ago. This token is a joint work with Felder and Polishchuk, where we propose a rigorous definition and show vanishing of I2. I start with reminding some basic notations of supermanifolds. In C infinity supermanifold, M of dimension Nm is a topological space with a sheaf of superalgebras, which is locally isomorphic to Rn with a sheaf of smooth function Rn tensor exterior power of finite dimensional space. I will always assume that our variety is oriented. The quotient of sheaf-based nilpotent radical is a sheaf function on this AC infinity variety M. So M is a closed subvariety of supermanifold. One example of supermanifold is you have any manifold M in vector bundle, which considered odd, you can construct associated supermanifold. For a supermanifold N with appropriate dimension and a closed subvariety, there is a well-defined open submanifold in M with corresponding body as absolute mark as a body, just removing from body of N a subset, subvariety N, but with no canonical complement. So lifting of subvariety is a choice of a subvariety, given subvariety inside of body of N, and they look for lifting as choosing of subvariety in supermanifold, intersecting transversely the body of N. And the projection is very simple. We have embedding of a body of N to N, and projection. The projection is compatible with our lifting if lifting is premature projection. There is claim that in C-infinity realm, any supermanifold has projection to its body, but it's highly not unique. And any smooth subvariety has a lifting was highly not unique. This lifting and projection are unique only if a odd degree is equal to 1. There is analogous notion of complex and real analytic supermanifold, but in these cases, there is no guarantee of existing of analytic projection of lifting. We'll need some variant of supermanifold, which has strange name, or complex supersymmetric set submanifold, which is a kind of mixture of real and complex stuff. It is real in the even direction and complex in odd direction. More precisely, you have a natural projection for exterior power vector space to C, 0 degree, and you take pre-image of a real. So complex supermanifold is locally ring space with body M, and structure sheaf is kind of small modification of a supermanifold. It's real, as you see, in all even direction, and essentially or complex in odd direction. We see why. Okay, and the quotient nilpotent radical with smooth real function of M. So you can talk about positivity in the sense that positivity of function on supermanifold okay, positive if its restriction on the body is positive. And there is analogous definition of analytic supermanifold. There is an important notion of completion. If you have a real analytic CS manifold, then the completion is a C infinity CS manifold and with corresponding embedding of real analytic ring in the smooth fields. The construction is not tautological, it always exists. The claim says that every real analytic manifold has a canonical smooth completion, not a difficult but not a trivial construction. Now if we start with complex analytic supermanifold of complex dimension, we can associate natural real analytic CS manifold. It is the following as a even part, it is just essentially your complex manifold considered as C infinity manifold. In other words, you consider anti-diagonal in the product your manifold in complex conjugated, and you take a restriction of on function on diagonal. As I explained, this defines a natural real analytical C infinity manifold. And as I said before, there is this canonical completion to C infinity C manifold. This will be kind of our player. So it is corresponding C manifold has dimension to n. It should be because you start with n-dimensional complex manifold. It's real dimension to n. But complex dimension is twice the odd dimension. Now the question of integration. Usually we consider oriented manifold, and if we have smooth oriented manifold and differential top form, we know how to define the integral. We could do the atlas. This that is well-defined definition of integral. Felix Berezin defined the notion of integration of a supermanifold. More precisely, he defined line bundle of superdensities on C infinity manifold, such that for any projection of supermanifold to its body, the push forward of Berezin shift is gives you a shift of top differential form of superbody. Therefore, if you have superdensity of the is a section of Berezin line bundle. If you take any Berezin superdensity, choose any projection, push forward of this projection in top degree form, and you can integrate it. The discovery of Berezin is that if your density is compactly supported, then the corresponding integral doesn't depend on the projection. So it defines, canonically defines, way to integral superdensity with compact support. The analogous one defined holomorphic Berezin line bundle on complex supermanifold, and the holomorphic section omega and Berezin define a superdensity omega, wedge omega bar on a smooth C-manifold, and we can define the corresponding integral. So we can integrate omega, wedge omega bar for any holomorphic superdensity on a compact supervariety. Now we come back to what we are for. So for any genus, there exists a complex supermanifold, which is the moduli space of supercurves of genus G. There exists a universal vibration, as usually comes in universal family. There exists universal vibration with fiber supercurves of genus G, and there exists analogous on Mumford isomorphism, which is you can say a section of Berezin on Fg tensor with fifth power minus fifth power determinant of push forward or relative Berezin line bundle. In super case is -5, in usual case -12, but there's not a big difference. Let nu G be their superdensity on our CS variety, delta of G. The alpha comes from Mumford isomorphism, and H is the determinant of the imaginary part of period matrix, as usual. Physicists define the contribution Ig to cosmological constant as the integral. The quotation marks around defined indicate the difficulty of providing a definition of these integrals caused by the non-compactness of a manifold Fg. Just some notations. The supermanifold has dimension 3G minus 3 2G minus 2 for G bigger. 1, x1 has dimension 1, 1, and x0 is a point. The corresponding body, the corresponding variety, is a finite unramified cover, or the modulus space, or modulus stack, if you will, of smooth curves of genus G. Now there are two classes of problems with the definition of integrals over non-compact supermanifolds. The first is specific for supermanifold, and the second problem related to necessity to regularize divergent integrals. This problem appears already in the usual bosonic geometry. Actually, the impossibility to resolve the second class of problems prevent the existence of the theory of bosonic strings. Let's demonstrate problems. First problem is easy to demonstrate. First class comes from dependence of the integral. So if you have superdensity of smooth C infinity manifold, you have to choose a projection P to body, take push forward, and integrate. I said that as your density had compact support, the answer does not depend on the choice of projection. It's not true if omega does not have compact support. This is a simple example. You consider the simplest possible manifold, 0, 1 class 2-dimensional, x0, 2-dimensional. Odd space, in other words, the algebra function is C infinity over 1 times lambda star of 2-dimensional space with coordinates. This you consider the simplest possible form. Now, for any function on 0, 1, we can define the projection, you have to define push forward of a coordinate. The base, the body is one-dimensional. Projection is completely defined the pullback coordinates. It should be even function. So pullback coordinate of x is form x plus some function f of x times theta 1, theta 2. And then you can easily see that the integral of push forward is f1 minus f0. We see that the integral depends on the choice of projection. Okay, in some cases, the following result clarifies the duality from density, which are in our case extend continuously to a compactification of it. It says, suppose you have a supermanifold, D is a closed subvariety on a base, we have some lifting. Then the statement, if you consider, so you have a super close super density on N, but it's not compactly supported on M. And then, like in our case, but then it's easy to see that integral of a push forward doesn't depend on the choice of projection under condition that is projection compatible with choice of lifting. The situation is much more intriguing, much less understood in the case when density blows up. So this is example which I can present, prove, cannot explain. So let's consider the simplest possible case once more. We consider our variety will be just a fine line across two-dimensional odd space, which means ring of functions is polynomial of x times lambda star. It means pre-image of d bar equal d. I said before, you have variety, fixed variety. On the body, you have chosen fixed lifting, and now you consider maps which preserve maps pre-image is lifting map into D. Let's consider this example. So it's always the same, but now our form has a second order pole at 0. And we obtain some function a of x. And then the situation is very strange. Now we are looking for projection such that we're looking for projection such a push forward does not have a pole. So the statement is that if derivative of A at 0 is not 0, there is no projection compatible with D. D is its natural pre-image of point 0, defined by ideal x equals 0. There is no projection such as push forward integral. But if a prime of 0 is equal to 0, then there exists projection compatible with D, such that push forward is integrable, just smooth. What is integral? Interesting, but for such projections, the integral does not depend on choice of projection. Just given very simple formula. So somehow, if your superdensity has poles, sometimes you really still can define an integral. And this what will happen in our case of computation of I2. So in this case, there exists a natural class of good projections, such that push forward is integral. And in this case, the integral doesn't depend on the choice of projection. Okay, now, first of all, we have to set up, we had some integral over open set, which correspond in the previous condition, integral over C star. We first of all have to embed C star into C, and we have to choose lifting, and this is done in general. And the first step of definition of an integral provide a construction of smooth computation of space by which we want to integrate. We construct a complement, which is analogous, in our case, to vertical space over 0, and we prove that Mumford isomorphism has second order pole along this divisor. This part is done for an arbitrary genus G. In the case of genus 1, there is one odd coordinate. Therefore, there is a canonical projection. So you can define canonically push forward to x1. It still has poles. But if you combine with then projection to moduli space, if you remember, we had our structure was the body xg had canonical projection to moduli space of course order G. If you combine this canonical projection to body of x1 with projection, you get 0. So it's reasonable. We can say that corresponding integral is 0. It's still slightly shaky, but makes some sense. We try to provide a similar description in case of genus 2. So from now on, I assume that genus is 2. I denote by Q of the projection. So the next step is a choice of smooth projection to body compatible with divisor. Now, there exists algebraic projection from a variety to body, and the Hockery-Fong proved that if you combine this projection with natural projection from x2 to m2, you get 0, like in case of genus 1. But unfortunately, the projection, this algebraic projection, blows up on the boundary D. So it's not clear at all why one could use this projection for a definition of the integral. We have seen that even in case when everything is smooth and compact, if you choose projection not compatible with boundary, the answer is not well defined. So let's start our approach. So let M2 bar be a modulus stack of curves of genus, of stack of stable, I wrote stack of stable curves of genus 2. D2 be the divisor of nodal curves. Here we have a lifting script D. Now, there exists an algebraic projection P infinity from the formal neighborhood of D2 in the formal neighborhood of D. It does not extend to algebraic projection of the whole moduli space, but well defined along divisor. This projection can be extended, not uniquely, to a smooth projection from this compactification of our variety to the corresponding compactification of a body. For such projection, we'll show that corresponding push forwards. In this case, it is not push forwards which well-defined push forwards combinations Q are well-defined form M2, but they still polar structure have poles. So we show that these forms are tame. I'll describe tameness later, and then define the integral IT as an integral. And we show that this integral does not depend on choice of extension. It actually vanishes for any choice. So now we essentially forget about super stuff, and we come to the problem of regularization with divergent integral. So the form which we interested on two blows up in a divisor in infinity, and we're faced with necessity to define the regularization of an integral. Divisor has two irreducible components, one of reducible and the other of irreducible nodal curves. I now describe two types of tame forms corresponding to these components in the process of regularization of the integral. We use this slightly toydist example in regularization in the definition of integral. So now there's some kind of general nonsense about regularization of integrals. So let X bar be complex analytic compact manifold, D a smooth divisor, kappa a top form, which blows up and defines. How does one define integral? One defines integral through a choice of cutoff function. And the cutoff function is a smooth function on the neighborhood divisor, which is non-negative, which is zero exactly or on the divisor. I should, zero is exact divisor. Hessian on this function is a non-degenerate Hermitian form on the normal bundle. And for any open subset, when you can give divisor with zeros of a function, the ratio mu to the bar divided theta extends to a smooth function on the U. Of course, this theta is not uniquely defined. Okay, we assume our function form blows up, but still, if you multiply a high power of theta, it extends to continuous function on x. Then you can define integral I kappa theta s as the integral of the product. Of course, it's a holomorphic function in the domain when real part is bigger than n. In the case when this holomorphic function extends to holomorphic function to half plane, where real part bigger or equal to 0, we can compute it value at 0 and declare our integral is equal to this. The problem is that even in this case, our integral even if defined, it depends on the choice of function, so it does not produce a definition of it. Now, two cases when it does. So one definition. A set of, suppose we have set kappa, some set of cut function. Could be one, could be many. Say this set of theta function, cutoff functions is adjusted if all these integrals are holomorphic at S and the value does not depend on the choice of cutoff function. A form is tame if we have an a priori defined not empty set or cutoff function adjusted to kappa. In this case, we define integral in natural way. One thing, a priori the set, depending on kappa, is not unique. You can choose different form. But in our case, which I present as very well defined set of cutoff function which you use. There are two cases to consider. I consider two classes of tame forms corresponding to two irreducible components of D2. Let's see the component of reducible model curve. So near C, the form looks like omega, which omega bar, where eta times eta bar, with eta is holomorphic form of a first order polynomial C. Okay. Now we assume C is a compact manifold. Divisor is a smooth divisor, which is product Z1, Z2. And there exists an isomorphism of a normal bundle. The divisor is a tensor product of pullbacks of line bundles on the corresponding varieties. Okay, let's capable set of top forms on X, which are the following. The product at 1 and at 2 bar, holomorphic forms of further order poles. Then we can take residue on these forms, so the top forms R1 and holomorphic forms on D. We can take a wedge product will be top infinity form on D, and I assume that push forward on Z1 and Z2 is 0. We consider a class of such forms. Let's now omega the set of all cutoff functions compatible with this structure. It means that corresponding Hessian on normal bundle is tensor product of forms on corresponding line bundles. The claim is that this set is adjusted. It means if you take any top form from our class, it means satisfying this condition, and you take any cutoff function, the integral does not depend on the choice of cutoff function. Now, there was important condition that push forward is equal to 0, and it actually, in our case, come from the statement that I1 was 0. This push forward is really interpreted in terms of computation for genus 1. So vanishing of the I1 for genus 1 gave a possibility to define I2. This is kind of, okay. Now there is another type of a another set of components. Now I describe tame function corresponding to component of irreducible. Form near irreducible to a form has a following product. It's kind of if Z is local coordinate of a component, with the form, it's nice smooth form omega prime over Z bar square, which is the same R or Z to the power 4, doesn't matter, divided to fifth power of logarithm. Logarithm comes from period functions. If you remember, in the definition of form, we have alpha times alpha bar divided by fifth power of h. H is logarithmic singularity, and therefore it has this form. So this is a kind of a form. Now, for any integer g, let's consider a space of germs of 0 of smooth to form defined in a small circle, puncture small circle on complex plane of the form. Such that omega prime is this form, where omega, when this omega prime, no, sorry, is such from omega that after you modify it by multiplication, z bar square times logarithm to the n, it extends to smooth form on disk, vanishing in zero. Sorry? I finish in 1 minute, and then we come. Just that set for L equal 5, as you remember, is used in the proof of obtainment. And the statement is that in this case, you can choose any cutoff function. The answer will not depend on the choice. The other thing is, I gave a definition. We choose coordinacy is actually the space is invariant under change of coordinates around it. It's called intrinsically defined space of tame forms which you can integrate. In spite of the fact that at first glance they have serious singularity at zero. On the other hand, if you consider a function, the same case, but don't put a condition that omega prime vanishing in zero, then one cannot define the integral. What is a physicist appeal all the time, that you see, this summation is push forward. Just 1 second. Yes, this push forward from xg to mg is summation of a spin structure. mg is a moduli space of smooth curves of genus. xg is a moduli space of curves with spin structure. If you look to component which kind of irreducible nodal curve, what happens is the following. If you consider projection on xg, this condition will be always satisfied. The only corresponding forms will not vanish in zero. Vanishing in zero is achieved only through summation of a spin structure. So summation of this structure appears in the statement that omega prime vanishing in zero.
Your IG is only defined over the smooth node, right?
IG is integral with small but you have to renormalize it. You see, let's go back to the stupid example. It's kind of, look to this case. My omega is defined outside of zero. I integrated out of zero. How I do it? As a pole of second order zeros. I cannot integrate. But by choosing a good projection, I did reduce singularities of the form. In this toy example, I reduce it completely and push forward as regular and can integrate. Non-trivial thing which I cannot explain without computation. That answer does not depend on the choice of projection. I'll be glad to understand it, but this is it. In the case of computational I2, situation is more complex. Push forward does not produce forms without singularity, but it produces some kind of tame forms, which in this case we know how to define singularities. So we expect this could work for higher genus, but we have not done it. Okay, I think it's end. Vanya, you had a question? I'm ready. Yeah, as I said before, second order waveform is true always. What is specific, and which will not exist, the existence of a projection, algebraic projection, in a formal neighborhood of a device. This definitely does not exist for higher genus. I assume that you don't need it. We really need smooth projections with some properties. We cannot right now formulate properties. We hope to formulate a notion of good, smooth projections with, so to say, sufficiently kill the second order polet over the second pole and reduce it to kind forms with tame singularities. This is not done, but specific thing which was used. It existed algebra. We have defined our projections as C-infinity projections, which coincide up to third order. We don't have infinity third order projection of a third order of a divisor, a supermanifold to divisor. There is no project, if genus is high, is was proven there is no projection of this super divisor to divisor. So you cannot have it. I hope that you don't need it. You really need to understand, and I think question is really understand not in super stuff, but in usual algebraic geometry, the notion of tame forms which could be integrated. We have kind of two examples, baby examples, but I hope it can represent some much broader class.
At the beginning, you discussed the notion of a completion, a smooth completion of an analytic variable. If you have a supermanifold, analytic supermanifold with dimension n/n, I assume your smooth completion has dimension 2n/2n.
Yes. So if I have algebraic, let me do it in two steps. If you have real analytic CM variety, we always can complete to smooth variety of the same dimension. On the other hand, if you have complex variety, you automatically produce CM real analytic variety. We're just taking diagonal and taking sheaf which come tensor product sheaf from both factors. So a two-step construction.
I assume the following doesn't exist, but I just want to know your opinion. If I take a complex supermanifold with dimension n/n, I don't believe it's possible to find a smooth supermanifold dimension 2n/n.
No, we don't look for it. A 2m, 2n. Because you take product, you see, I don't look it because I want to take tensor product of densities. And density has 2m variables. So what you are asking, I agree, doesn't exist, but I don't need it.
So should this integral have a homological eventually?
There is very interesting question. Since you see, let me stop there. Even in a very simple, the first case of tame varieties is very easy to describe. Very natural. Divisor is a product. You take forms, kind of no logarithms, put some conditions. I don't know the homological definition of this integral. I'm pretty sure it should exist. I can give you procedure. I can prove it will define. I cannot. You really don't need that your form is eta times eta bar. You can take any C infinity form of this type of behavior near infinity. I can produce a corresponding number. I'll be tried, it failed in my attempt to interpret the cosmology. I'm sure progress lies in the finding of cosmological interpretation.
So, in the work of Docker and Fung, they had, on the genus 2 moduli space, they had a homomorphic projection to the moduli space of
Yes.
the spin, and then you can sum over spin function.
Yeah. It blows up at infinity. It does not extend to map on infinity.
Projection that they discussed blows up at infinity.
Yes. Therefore, you see, even as I say in very simple FC infinity case, using projection not compatible, don't produce correct answer. So
Not only is that true conceptually, but actually in my work I showed examples of what happens.
Okay, let's talk. It's going to become it'll be great to talk, but I just want to say, technically, the most technically complicated part is to prove that our projection produces the same answer in their projection. It's a very delicate analysis of what our new.
I think I know what the question is probably be. But in your presentation, I couldn't see that the Docker-Fung computation was part of it.
Sorry, you could not?
I couldn't see why the Docker-Fung computation was part of it. Conceptually, what I think what we should have done is the following. Docker-Fung did a computation which gives 0 by summing over spin function, but without carefully treating what happens at infinity.
Yes, yeah.
Carefully treated what happens at infinity, and it should have had the. I imagine the logic is that we showed that the correct computation at infinity produces no correction probability.
Correct. What happens is the following. We took just a path between his of course everything is like behavior at infinity. Outside infinity, we took a path between his and ours and computed derivative of a difference. And in this time, by unpleasant explicit computations, term cancels. But there is no a priori reason for them to cancel.
I have a few remarks about that. I'll just take one of them now. We can discuss more later.
Okay.
If instead of R10 you consider R4 times the Claudian module, then in general the two computations dissipate. And the correction between them are actually computed with one computation.
Okay, we can try to think about it. Great. I really think, okay, this is accidental. From our kind of computation, it came not naturally, but just result of work.
So what came that you say is not?
We say that the thing that the Hawke conjecture and our projection gave the same answer is not explained. It's proven, but not explained in our paper. We just take a very concrete realization of Q cover or of P1 and things that you use. We just use this dirty job of computing, you got 0. But the feeling is that slight variation would be very interesting to consider your example. Okay.
You mentioned one other thing that's perhaps worth mentioning. You mentioned M1/1, but one can consider M1/0 with an even spin function, where the moduli space is purely bosonic.
Yes.
And then the sum of the spin structure vanishes.
Yeah. Let me see. I would say that when you have only one fermionic direction, it really does not matter. Does not matter because projection is canonical. So it does not really matter. Nothing happens. It happens exactly the same. I don't know physics, but in terms, it's just essentially direct product. It's isomorphic to vector bundle.
I'm saying that in your present, you might perhaps there's something. Maybe we should discuss this.
Okay, let's stop. Fine, let's stop.
There are more questions in the room.
Can
Yes.
I give a very small comment? It's not a question, but I give a
It's
comment.
better.
Okay. So in a series of papers with Yao, we calculated integrals over moduli space of superstable maps. And these also relate to moduli space of superstable curves.
Okay.
It's not a projection map, but it's actually a localization. So we define the torus whose fixed locus is this regular moduli space.
There is no, I understand. The moment you have enough symmetry,
Yeah.
such that fixed points are compact,
Uh-huh.
then not that I can do something, but can easily imagine doing something.
Okay.
This is the case when there is no symmetry.
I see.
You cannot. The moment you have a
Okay.
symmetry, if you consider equivariant cohomology, you immediately reduce to fixed points. Everything is well defined. And then you have some way to come from equivariant cohomology. If something is sufficiently degenerate, you do it.
Okay. Yeah.
The difference is there is no symmetry here. We really deal
I understand.
with non-compact.
Okay, great. I understand. Thank you.
Any more questions? If not, let's thank David.